Euler's formula, e to the I theta. We know the Euler's number is a limit as n goes to infinity, something like that. However, it is very useful to consider the exponential function and even the sinusoidal function. Let us prove this is true. There are so many ways to show this. For example, we can expand e to the I theta from this definition by making use of binomial expansion. We will find that it is a kind of power series and we can divide this one into two pieces. One is even powers, and the other is odd powers. And even powers and odd powers are collected separately, and even powers become this kind of form. Odd powers become, because I 2k plus 1 equals I minus 1 to the k, we have additional I. And if you know how to expand sine and cosine, it is easy to show that it is cosine sine theta plus I sine theta. We have a different way today by making use of the integration. And actually it satisfies a very simple first order differential equation. And first order differential equation is solvable simply by integration. And that integration is possible by separating variables. For example, df over f becomes I d theta. This depends on f only. This depends on theta only. If we integrate, it becomes a log. It becomes a theta. The inverse function of log is nothing but exponential. This is a very simple proof. We like to use a kind of awkward way. However, it is very useful to understand the nature of the simple harmonic oscillator. So if we repeat this operation twice, then we take the derivative with respect to angle twice. A single derivative will bring in I, that is a square root of -1. And repeating the operation, once again, we have I squared. Because I is the square root of -1, you will arrive at negative sign on it. We can move this one to the left-hand side. You finally end up with a very interesting equation that originates from the simple harmonic oscillator. And mathematically, this is something like a circle equation. You know, the solution, the point, general point on a circle centered at the origin is expressed in terms of cosine and sine. And this satisfies, this one is set, you know, the Pythagoras theorem, cosine square times square theta equals 1. This equation and these equations are very, very similarly equivalent one. We recall how to compute the cosine and sine's derivative. And cosine becomes a negative sine, and sine becomes a positive sine of cosine. They are exchanged and irregularly changing its sign. If you did operation twice for the cosine and sine, you arrived at the same result. Even though a single derivative has a different sign, if you apply the derivative twice for the cosine, either cosine or sine, the result is always the same as the original function with the negative sign on it. As a result, move this one to the left-hand side, you will find both the cosine and sine are the solution for this differential equation. So cosine theta differential equation can be expressed in terms of this kind of operator applied to f of theta. If I apply this, you will find 0. So I substitute C1 plus C2 sine theta into here. Because this one gives a 0, this one also gives a 0, the linear combination of cosine and sine will also give 0. Therefore, we can say these two are made up of a linear combination to construct the general solution. The reason why we claim it is a general solution is that, first of all, cosine and sine, they are not linearly dependent. There is no way to express cosine in terms of sine without translation or magnification. So these two are linearly independent functions. And as you know, this equation is solvable by taking the integration twice. In each integration, you have a free parameter that is called integration constant. The two integration constant is related to these free parameters. Therefore, there is no way but to have your solution in a linear combination of these two linearly independent functions. That is a general way of solving the second order linear differential equation. If you have a maximum derivative of triple time, then there will be three independent parameters, and that corresponds to the three linearly independent solutions. If you have found the same number of linearly independent solutions, then you just multiply arbitrary parameters on them and add them up, and you just apply the initial condition or any kind of boundary condition to determine the exact solution, and that one is uniquely defined. Therefore, f of theta should be a linear combination of this. And then its derivative, as far as the sinusoidal functions are concerned, I know how to take the derivative. And I know the exponential's derivative is very simple. Using these two conditions, I can construct the initial condition, for example, at angle theta equals 0. At theta equals 0, this function should be 1, and its derivative should be I times 1. As a result, I can determine these coefficients to finally determine the expansion of e to the I theta to be cosine and I sine. In comparison with this expansion, we already, let's see, expansion we already have considered. If we compare this result with this, I can identify, even though you don't know how to expand the Taylor series expansion of the exponential function and the sine or cosine function, this one is identified to be this, and this one is identified to be this. Okay, anyway, we begin with the definition of the Euler number to consider the power series expansion of the exponential function without knowing the Taylor series expansion. Eventually, it is exactly the same as the Taylor series expansion about x equals 0. First of all, we consider the case e to the 0. Any number to the 0th power is defined to be unity. Next, we assume that x is positive, then we attach an exponent called x. Law of exponent says something, we just attach the power. This one initially has a power n in it. So x, so multiply two exponents, I would get this nx. The limit should be the same for example, I can take the limit as n goes to infinity, but it is equivalent to say limit h goes to 0 and it is 1 plus h and 1 over h. And because the limit exists, I don't have to worry about whether I have to choose the integer or not. Any real number approaches infinity, that's okay. So I would rather rescale this n as an x as long as it's a positive. As n goes to infinity, nx also goes to infinity. If x equals a negative, that it should reach minus infinity. You should be careful. And then why don't we redefine this nx by n prime, something like that? Then we multiply x or x over x, and this goes to infinity. So this one is redefined by new n. So this n and this n, these two n's are different. As a result, I know there is a new factor of x in front of 1 over n. So when we derive the expression that e equals k runs from 0 to infinity 1 over k factorial, we made use of the binomial expansion. And applying binomial expansion once again, what we reach is this expression. The same is true, all the same as what we have done with the derivation of explicit evaluation of Euler's number. Eventually, we will find if you have taken the calculus class, you will find this is a Taylor series expansion of exponential function. We can extend this idea to the negative value, and in that case, I can replace this one with this kind of expression. As you know, our power becomes negative, and this x over x, but we know nx goes to infinity, n goes to infinity, because x is negative, nx goes to minus infinity. So I have to consider the case, some power should go to infinity. Okay, so it still goes to infinity, but it is minus infinity. N goes to infinity, but the power goes to minus infinity. As a result, this one goes to negative infinity. By the way, what we have to use is different from what we have used for the derivation of positive case. That is a binomial expansion. What's that? In here, in case n is a real, n is a integer, we can do the same job because there is a factor terminates at some point. However, if it is in general not a real number, then this method does not work, and we have to make use of the binomial, a generalized binomial expansion developed by Newton for the any real power. In any case, that's up to you to consider the mathematical details of a rigorous mathematical derivation for the general case. In physics, we we are much more interested in the result. However, this kind of rigorousness should be enough for your derivation of any physical quantities.